So friends, we are on our core topic, that is probabilistic risk assessment. We have already discussed probabilistic modeling. Here I would like to make at the outset two statements. Quite a bit of tools, that is fault tree, event tree, and thing that will be discussing here. It is just for the sake of continuity. Otherwise, we have discussed these items in dependability engineering. I think that was second lecture. You can see that. And second thing is, I will be devoting more time on data analysis and how to collect the data, because as I told you, if the data is quality data, then probably we will be able to have a better PRA model, justified PRA model. And I had also stated that maximum effort goes into data collection and analysis, so that will be reflected in this thing. So one situation you will find that I am going little fast compared to my previous lectures, because this presentation is little lengthy. So let us go ahead and without wasting time, major steps in level 1 PRA. So first is, what are the events that are possible in a plant. Okay. So here we have formulation of a list of initiating event. Initiating event means, as to loss of offsite power, loss of coolant accident, loss of regulation accident, and every industry will have its own characteristic of event. And that plant specific generic master logic diagram will be the process that will be used to get to this list of initiating event. Okay. Then development of event tree for the accident sequence analysis and system modeling and using fault tree analysis. So for system modeling, fault tree approach, and for event tree for plant level modeling, that is event sequence modeling. And here we will come to one stage where qualitative analysis approach has been done. Now next will be quantification, and here, as I mentioned, you will take quantification some time. So that will be covered by two data collection and analysis and quantification of the model. We have come here, and here the Monte Carlo simulation will for characterizing uncertainty and sensitivity analysis. So that means when we do a PRI analysis, Monte Carlo simulation, and along with that the Boolean logic, which provide the logic for creating or reducing the fault tree to its because it is a very computationally resources intensive exercise. So these two are very important. One is Monte Carlo simulation, and other is reducing or getting the list of minimal cut set along with its quantification. And those cut sets, they represent the major results from PRA, apart from that integrated statement of risk from the plant. Okay. Now initiating event can be classified into internal event, that is one, and external event. We will be confining ourselves only to the internal event, level 1 PRA with limited this thing. So loss of offsite power, and we will be giving explaining everything through loss of offsite power, loss of coolant accident. It could be major, minor. Actually, the list of in the plant, the list contains more than 25 to 35 initiating events. We have seen the major class of events over here, and that too are not a complete. So you have loss of flow accident, loss of regulation accident, internal flood, and then internal fire. They are there, and then external events called seismic event. It is an external source which affect our plant operation, and then external fire, external flood, and external object or impact. Any impact of object from the outside. And then identification of safety function. Once we identify the initiating event, it becomes easier to identify the safety function. So for primary shutdown system, the first system which will come are when the plant safe shutdown has to be achieved. If this system is not coming, there is a second system which will come into action. Normally this system may or may not come, but primary shutdown system comes, or if it doesn't come, then it will come. Then shutdown cooling system. Now there are two functions. The heat production should stop. So that happens through primary shutdown system and secondary shutdown system. And then cooling is another. So now your shutdown system is our, let's say, loss of offset power. Power supply is cut off, major power supply is cut off. So the plant has tripped or shut down. Now, but still it keeps producing the decay heat. So for removing the decay heat, the shutdown cooling system is there. Suppose if there is any problem here, then emergency power supply. So emergency power supply system is there. Not for this, for acting as a source for these kind of systems like cooling system and all that. And the emergency power source comprise of class 3, class 2 and class 1. That is class 2 AC and class 1 DC battery banks are there. Emergency core cooling system is the system when it comes into action when there is a threat to the core cooling, either through leakages or any other loss of flow type of situation. So mostly during when the coolant loss is observed from the system, then these systems they come into picture. Okay. So we have failure of process system lead to initiating event, and we have safety system when any process system generates a trip. So system the safety system should come. Now as I told you, the fault trees have to be reduced to minimal level, minimal cut sets, minimal number of components that lead to the top event. So that is called minimal cut sets, and there are laws for this. So this is a cumulative law. So here A into B, B into A, and just position they are changing, so no issues. Okay. Associative law, A plus B plus C, A plus B, it is association is here. Then also they are equal. So associative law, A into B into C or AB into C. So bracket, no issues. Idempotent law, A into A is equal to A. This is the most used thing in cut set reduction. Two failures reflecting in two branches of fault tree, and they have to form a single basic event. So absorption law, A into A is equal to A. This is the dominating governing number. A into A plus B is equal to A, because A is dominantly appearing here. So dominance has to be seen. Distributive law, then A into B plus C, AB and AC, okay, or AB plus AC. So since A and A will appear here, it has been put into one, and then BC is there actually. Complementary law, A complement of A is equal to null set, and A plus complement of A is equal to universal set. De Morgan's law, complement of A into B is complement of A to complement of B, actually it should be B, and complement of A plus B, complement of A plus B is equal to AB. Okay. So this mathematics or Boolean logic is used to reduce the fault tree size, and so there will not be any repetition of the component in various branches of the fault tree. Okay. And then Monte Carlo simulation. These two together makes the fault tree or PRI model development. Event tree modeling and analysis. We know that event trees are modeled at plant level, and they are basically to see the propagation of scenario when a initiating event occurs, and the plant response in terms of safety system operation which were standby till the event had occurred at time t is equal to 0. The moment event has occurred, the system based on applicability of the scenario, they will be activated, and that response will determine the accident sequences. Okay. So this is the function of, so event tree is nothing but a graphical model how the event scenario propagates. Let's say loss of upside power. the first thing we would like to have is the plant should shut down and the emergency power supply should come into the force and then take care of cooling of the system or remove the decay heat, because plant has already dipped automatically. So let us see the inventory. So here we are dealing this inventory at qualitative level. Here when I say loop is loss of upside power, the initiating event has occurred. So the shutdown system number 1, there are two, see the kind of redundancies built into the system, shutdown system 1, shutdown system 2. If this comes, it's okay, otherwise this will come and it will take care of safety. So success is on top and failure is on towards bottom. So loss of upside event occur, shutdown system 1 has successfully activated, so it will go on top. Emergency power supply system is activated, again it will go top. Shutdown system, it will shutdown cooling system, it has got activated, so we are safe. So the consequences are safe. Okay. Now suppose if the primary shutdown system did not come and secondary shutdown system had not come, then we go into the emergency scenario, severe fault damage. Now remaining thing you can model it. Suppose if shutdown system 1 has come, so shutdown system 2 we are not depending. So here now we go and emergency power supply system doesn't come. So the accident sequence become loss of upside power, shutdown cooling system. It is unsafe system because cooling is very much important, for the plant. Similarly, so all this thing can be mapped on this and safe and unsafe state. Let's say for example this one, event number 4. So you have accident sequence number and their characterization, okay, and then you have consequences, safe, unsafe, threat. Threat is slightly that it will happen after some time, something. Emergency power supply system, loss of upside power and emergency power supply system. So if that has come, there is a threat to safety. And if loss of upside power has come and shutdown system has not come, but shutdown system has come because it is not appearing here. So shutdown system 2 has come here. So it is a safe state. So that way you analyze everything, you have consequences, you have frequency. These two things will be analyzed in the next slide, and we'll devote a lot of time for this analysis. So you understood the qualitative level accident sequence development. Now let us see what happens for fault tree analysis. Fault tree analysis, this also fault tree I think we would have used in our earlier systems. So we have fault tree, and here we have this class 3, that is you read it as a emergency power because we have used emergency power system. Okay. So emergency power systems failure, and these are the various components that we have over here. Diesel 1, CB circuit breaker 1, common cause failure of DG, and then okay, and then under voltage on bus D. So there are 2 buses of class emergency power supply, and this fault tree, once we reduce it using the Boolean logic, it transformed into, you can see how simplified it has become, independent failure and common cause failure. Okay. So DG1 train, DG1 and CV circuit, either in that train there are 2 diesel generators. So in train either DG1 fails or DG2 fails or its associated circuit breaker fails, then it is a independent failure. And finally, so here you would like to underline the importance of common cause failure, because they are, even though they are fraction of the independent failure, but finally they will be the dominating factor most of the time actually. So one has to be very careful. Boolean logic, we got this tree. And now what happens to this? Let us see. For quantification, now what we do, we had qualitative discussion, and this fault tree was discussed I think in dependability analysis or some other places. So now source of data. Please we have to pay attention to this very much, because plant specific source is the ideal thing for developing a PRA model. Data from similar plant is another option, and generic source is the option when we are having a plant at design stage. We can use it, but the moment it is in operation, we have to use it for plant specific data only. And handbook approach, this applies to electronic component, and sometimes for mechanical component also, but popularly mil 217 plus or present one or F, they are used, mil 217 plus or F, they are used, and quantification. So, how we do plant specific data? Data collection and analysis is important part of it. Estimation of unavailability of component. We'll see the formula how we do that. Accident sequence analysis and uncertainty quantification. These are the 4 steps that are there for quantification. How these 4 steps are coming? Plant specific data, there are many points I have indicated here. We should have a first of a data collection format. Data should be collected, and we should be very particular about the common cause failure data, and human failure data. Okay. And the component specification, if we take data from generic source, to the extent possible, we should do component specification matching of the data, so that we get, even if it is not available plant source, we are trying our level best, and we are doing our best to get the correct data. Then quality assurance program, it should be part of this thing. So, computerized data collection format, then quality assurance program, then train team, and then identification systems for raw data. Raw data is not coming in the way we can directly use it. Lot of refinement, analysis, filtration has to be done before we make reliability data for our PRA application. Then specific activity data are fault, build and operate. So, what kind of failure modes we are looking for, that failure mode only should be chosen, or data should be collected. Suppose if we do not have information on failure mode, conservatively all, we will see in next slide what kind of options that we use, and the data collection procedure should be approved at highest level in the management and should be followed. Now, plant specific data, major features of there is reliability data management system. Okay. So, this kind of system we have to develop, and then we have to develop plant coding. Okay. Plant coding means component coding, because each component should have its own code in our database. Creation of relational database is very important, so that we can see the cross check from one file to another file, and that should be done right in the beginning. If we do not develop a relational database, then there will be problem. So, pre-processing of data, raw data obtained from the field, categorization and level A analysis, data applicability, data binning, these are all form, we can just see this type of thing, and reliability estimation. Okay. And final database integration with the PRA software. So, all this normally for probabilistic risk assessment, there are professional software, commercial softwares are available, and it is advised that for small system we can do analysis, otherwise the cut set analysis, Monte Carlo simulation, it is very involved job. So, professional software should be used for PRA. Now, I discussed that importance coding system. Coding system means, let us say the first 2 digit in coding system should go to the identify the plant. I have 3 or 4 plants in my country or in my organization. So, then which system the component belong to, then what type of component is this, a pump, it is a centrifugal pump, reciprocating pump, or what type of pump, then type, component type, then plant designation, component designation. Okay. So, and then I have explained here, this is a code for component in plant P1 having emergency cooling EC system, centrifugal pump PC, described by injection pump IP number 1. So, in one string you will get all the information, and that is very useful for a PRA modeling. So, we have to follow this one, and then there is a failure mode characterization. For failure mode characterization is, this is a table I have taken from International Atomic Energy Agency document, and you can see here all modes of failure if we are not able to zero down, degraded failure, fail to. So there are some for mechanical fail to remain open. Okay, it is for one check valve or it is for some electronic circuit, fail to close for mechanical valves, short ground, it is for some electronic or electrical circuit. So for various component in the database, we have given the failure mode. If our failure internal leakages, then rupture, fail to start for pump or wall, this thing. So, we can use this and use it in our coding, so that by looking at this we can make out what kind of data and what is the failure mode, which is a very critical information for any component database we have. So typically how it looks like the database. This is IEEE Tech Doc 478, and then first they have identified a component, that is battery, its code, component boundary. Okay, in database it is very important to demarcate the component boundary. If I am talking about pump, whether motor is a part of the pump, or if it is a cables which are running up to the junction box, that is boundary, or it is going to the starter for the pump. So we have to, otherwise we should not be double putting the component, or we should be having a clear cut boundary, so that when we do the analysis, we are able to capture the right association. So defining the boundary is very important. And generic mode, then failure rate or failure probability. You see here they have given the uncertainty bound also, that is mean value, and then lower and high value and lower value. Repair time, typically how much it takes, data collected from root source, and all those characters. So typical, this is a typical card in IEEE 478. It is available in open domain and you can use it. There are many databases that are available. You should you have your hands on the right database that is available. Now final data structure in a database is a component generic name. What is the generic name of the component? And as I mentioned in the previous slide, what is the failure mode of the component, fail to start, fail to run, system, which system it belongs. So this information, component boundary, type of service, continuous or standby, operating environment, control room environment, it is a service area, harsh environment, accumulated time, accumulated demand, failure rate, failure probability, uncertainty estimate, bound, upper bound, lower bound, name of the project part. So, and then some special type like Bayesian updating has been done if the data were not adequate, then Bayesian. So as I told you, advanced techniques will have to adopt when we do not have data. Bayesian updating is one of the data. It is for your homework to find out what is the Bayesian updating. I have limited data from my plant, and in generic data source this data is available. So I have to combine these two. So Bayesian updating is used in such places. One is the prior information and the evidence, that means my plant expense. So this I will use and I will estimate the posteriori lower bound, upper bound, okay, median and lower bound and upper bound. So this is the how. Now for component there are different type of component. So continuously operating system, non-repairable component, the failure model is this. For repairable system, the failure time to repair is, mean time to repair has come here. For standby system, random failure during standby condition. So this is the model that we have, and then lambda s is the standby failure and t is the test interval. This standby failure components are tested periodically. Okay, so that test interval will come into picture. Okay, now. And then unavailability, now for standby tested component, Q is the override availability, and tau is the average test duration. Override availability means it is the period which has been taken for its unavailability. That means we are not bothered about whether this component is available for this particular duration, and that factor has to be there. So tau is the average test duration, and Ti is the we can say test interval, whatever we have. And then contribution of repair. So lambda standby failure into repair, so mean time to repair, and then contribution from schedule maintenance. So Fs, that means component failure probability into maintenance time. So test interval, lambda is standby failure rate actually. Okay. there are certain components for which electronic component, we have to pick up these components and do. So there are two methods defined by MIL 217, as I mentioned earlier. Part count method, that means you simply count part and try to assess the, that means complexity is describing the failure rate. If the parts are more, then failure rate will be more. And for part stress method, so this is microchip, this formulation has been given, and this is lambda p is part failure rate. That means C1 and C2 are complexity factor, this is the number of pin, and this is complexity, that number of transistor, number of gates they are there in the device, and this pi t is the temperature factor, and pi e is environmental temperature, quality factor, learning factor. And these factors we have to use for our plant, and we can for this is a model for microchip. Same way model is there for resistor, capacitor, and all electronic or electronics component. We have the model and we can use it. Of late, the physics of failure approach is being used for electronics systems, and this is that involves environmental testing and creating a model, lifetime model of the plant, and then it is also called science based approach. So what we have is empirical approaches where some components were tested and then their failure rates so were estimated, but nowadays there is an emphasis on physics of failure approach for electronic component reliability, especially in reliability analysis. Now we saw that fault tree. Let us see, I have come back to the fault tree. Now data analysis is over. We got the DG failure rate, demand failure probability is his for circuit breakers 7, 8, 10⁻³ because both the circuit breaker DGs are similar. DG1 was having a lesser demand failure probability compared to and common cause failure 2 into 10⁻³. It is nothing but fraction of 0.1% of this data, and with this we have done the analysis of this fault tree. That means now we are into our quantification era for this same fault tree, or it is, you can call it as a emergency power supply failure, okay? Because in earlier example this was a emergency power supply failure. You can see that common cause failure DG is dominating. Then we have DG1 into DG2 together failure. This second cut set with the two component 1 into 10⁻³ circuit breaker and DG2 failure. So these are combination of component failure or single failure that is taking you to the top event. They are called minimal cut sets, you know, cut set or minimal cut set. Actually they are minimal cut set because we have analyzed them. So with this we estimated the failure probability 3.2 into 10⁻³. Okay. Now regulatory estimation for emergency power or class 3 power is 1 into 10⁻³. That means we are very close to this figure. So the message is that we have to improve this system, but it is not much away from the target value of 1 into 10⁻³. So this is one advantage. And when you use this result in our event tree, we saw that event tree. Again, the primary shutdown system nomenclatures have changed here little bit. Secondary shutdown system, I have used here human action, but the procedure in basically it remains same actually, you know. So for class 3 data I have input here, and after doing the accident sequence analysis, I get these are the cut sets, you know, loss of offsite power, safe, and then threat and all those things we have done. This analysis is not exactly different. The name nomenclature have changed, but methodology remains same. Emergency human error has been one extra element has been taken in the here. Decay heat removal system. Okay. So and now we got the core damage frequency, because things which are failing in unsafe manner, you know, safety, threat, safe is okay, we'll avoid, and core damage. So CD is the core damage. Core damage means some damage is occurring because of these events, accident sequences. So all CD value will be added up 1. So severe core damage for the 13th event will be this one in the event tree, and we have here 1.92 into 10⁻⁷, CDF loop, and this one plant this one. So core damage frequency comes to 6.2 into 10⁻⁶ from loop contribution. Okay. In the previous slide, we discussed how to arrive at the statement of core damage frequency, and we saw the figure was 6.2 into 10⁻⁶ plant per year. Okay. Now the next step is accident sequence quantification, in the sense that we did the quantification, but we are trying to arrive how much the loop contribution is there to the total core damage. So we know that the core damage frequency, as we can see here, 5.25 10 to the minus 5. Okay, and now we have the loop contribution also with us. So that means we have two figure, that is contribution of from the loop, which we discussed in the previous slide, and now core damage frequency. These two we have. So we'll see loop contribution to the total CDF, which is nothing but 6.2 10 to the minus 6 divided by 5.25 into 10 to the minus 5, and which comes to around 11.8%. So this is the loop contribution. That means this figure is very important. This exercise has to be done for all the accident sequences or all the initiating events, rather, to see how much these initiating events they are contributing to the total core damage. So here loop contribution is 11.8%. And further, now if we look at this loop figure 6.2, now major loca is here. This figure we have taken from the reference studies. So loop is the only new thing in the list, and now we see that the total contribution is 5.25 10 to the minus 5, which is the nothing but the original figure, and that's how we have this estimates over here on this slide. Now what you saw is the point estimate of core damage frequency and various contribution, which I am again repeating in this slide. Now, but then whenever we provide any estimate in probabilistic studies, it will be more realistic and effective if we can assign the uncertainty associated with the distribution. So there is a procedure called Monte Carlo simulation, wherein the whole PRA model is subjected to random initiation at various points. So you can see on the right side this figure is there, and this curve is generated using Monte Carlo simulation. So the advantage of generating this curve is that we have the uncertainty characterized by a lower bound, upper bound, and then we have mean value also. The peak will show the, actually in log normal distribution we take the median value instead of mean value. So the peak value will indicate the median value, which we can see on the CDF, that is x-axis, and these are the frequencies. So in short, Monte Carlo simulation to assess the uncertainty. So we get median value, lower bound as well as upper bound also. So here 5% makes the lower bound and 95% makes the upper bound, and this range is 90% range. It is 90% confidence interval. Now, insight from level P. What is the insight that is available? Total CDF is one of the major insight, that is 5.25. If the target is, let us say 10 to the minus 5 for the plant, then 5.25, slightly more, but it's okay. But for new plant, the core damage frequency is 10 to the minus 5 is the target level. For advanced plant, it is 10 to the minus 6. So if it is an advanced plant, then we are slightly more. But if it is the old plant, then we are very close to the target value 5.25. I mean, not close, slightly higher. So we have to look for some improvement. So for second generation plant, CDF is expected to be 5.25 into 10 to the minus 4 plant year. So we have first generation, second generation, third generation plants. Okay, the distribution of events in terms of CDF in rather well spread out, presents well balanced design and all that. Individual plant contribution, CDF is more than 35%. Okay, so the present CDF estimation can accommodate the full scope level 1 PRA input, still complying with the CDA target actually. Okay. Then the uncertainty bounds are only representative and to have been illustrated to cater to this thing. So these are the insight that we have. What are the uncertainty, what are the core damage, what is the fraction, how much total contribution is there, and then the quality attributes meet the PRI standard, because our uncertainty bounds were very less, and then this can be used for risk monitor and risk based in-service inspection. These are various application areas these data can be used. Okay. And of course, in PRA, documentation forms are important. You can just go through it, and system level, system analysis format, main executive summary, they are the major element of documentation. Format for the main report, quality attribute and checklist should be there. Then only these reports will qualify for regulatory review. Okay. So this is one thing. And then overview of level 1 PRA. PRA is a core component of risk base and ORCOM. A quality PRA only qualifies for consideration of application. The quality of data and completeness of model, including the list of initiating event, is critical to PRA. PRA process is iterative in nature. Monte Carlo simulation is at the core of PRA. Now, in next presentation, we will be discussing the major elements and functions in integrated simulations.